See, I don't give a crap on recording. Actually, I do give a crap. Fuck it, I don't give a crap. Check my emails, I don't care. I should probably care. Fuck, well, it's too late now.
It's okay, man.
It's too late now. Hopefully I don't have anything bad.
You can do worse than what I did, man. This interview.
I just remembered. Look, that's so
Yeah.
right. Close share tray, open share tray. Share.
Let's be because the room
Dude, fuck it. Oh, look, there's people. Dude, we don't have the banner up. Why are they tossing up with the banner up? Okay, you have this. No, I dropped it outside. I'm gonna go welcome them on. What were we missing? We were missing something.
Oh, good. We need stars, huh? My screen sharing? Am I screen sharing? Problem?
Yeah, I mean, your screen is showing.
Nice.
No one's here. Nobody knows about the link.
Do you want to post on Discord? Is this in presented? This isn't presented, right? What is it?
No, it isn't in present.
Okay.
How can you share the link?
I'm gonna start it. Is that fine?
Yeah.
Good morning. I'm gonna send the PowerPoint right after. I'm in sweatpants. I'm good.
I'm dressed up.
Alright, I'm gonna introduce you as a smarter, funny, and good-looking person more than me. Alright. You're really good. Because like everybody's on the computer. Let's start. Green light. What? Oh,
Shit, that's right on the other. Sorry, guys.
That's the cue. Everybody knows the music is out. Part of the start. Mic test. Mic test. Okay. And then you let people come in. There you go. All right. Hello, everybody. Welcome back to another workshop. Thank you very much for coming again this week. I'm not going to lead this workshop. As you can see, I'm dressed in sweatpants. Not looking good for this. Yaku is going to present this workshop. Yaku is a much smarter, good-looking, funnier guy than I am, so he's going to do a fantastic job. Before I do go, I do have to make a small announcement. I know you guys a little bit. Hack AI 22. It's sold out, which is incredible. Thank you so much for those of you who signed up. It's going to be a really good event. I did want to say that those of you who did sign up, please check Discord tonight and the next days. I'm about to send an announcement through there. If you aren't part of our Discord, scan this QR code very quickly, join our Discord, because that's where we're going to be running the hackathon and all of our other events run through Discord. So please do join our Discord, especially if you're on Hack AI. If you did get a ticket, please do go, because we have a massive waiting list of like 40 people. And unfortunately, they can't come. If it were up to me, everybody would go, but ECS is putting a limit to 150. So that's that. Okay, enough marketing. Jakub, I'm going to pass it to you. Good luck, and hope you all enjoy.
Hello everyone, hope you can hear me all right. So, from last time, we did the forward pass. So we had our output, we calculated our output, but we didn't know what the weights were. Today for the back propagation, we're going going to find out how to find the weights and why we should do them. So you've seen this diagram probably everywhere. Is we've got our nodes and we've got our edges representing the weights. It doesn't give us a good insight of everything more happening inside the network, like biases and activation functions. So we found we like a different representation inspired from the YouTube channel StatQuest with Josh Starmer, and it presents it in a much better way. So we have the weights on the left with a multiplier box. So firstly, these weights we have to multiply them by the input, followed by the biases. So these are added, and their output, after we've times it and added it, goes to on the graph, this is the activation function. So we read off the value on the x-axis, and the corresponding y value on the line, and this will be the output of our activation function, which is again times by the next set of weights on the next hidden layer. And we have output layer with the final bias, and that'll be our prediction at the end. So you can see we've got our padlocks here. So the weights and the biases are unlocked, so signifying they can be changed. That's what we're going to be changing around this workshop with backpropagation and gradient descent. However, the activation function, in this case we're using soft plus, which is similar to ReLU, which we used last time, where we have a constant gradient after zero. This one just slightly changing with a gradient in the middle, so it might look nicer on the slides. And finally, of course, we have a loss function. In this case, we use sum squared residual, which is similar to the RSME one from last time. However, instead of taking the mean of the squared values, we're taking the sum. So previously, if you remember from one of our new workshops, we did linear models. So we did gradient descent in that one as well, but we only had, instead of a whole neural network, we only had one function, y equals mx plus c. So you can think of this as the m, the gradient, being the first weight, and the c being the first bias. This is the same concept applied with propagation, however, we're much further in this workshop. So if you remember from high school, we have the chain rule. So dy over dx equals dy over du over dy over dx. So you could probably simplify this down to timesing two differential functions and thinking that the du term is cancelled out completely, rather. So we have a bit of a problem. We can't start from the start, because if you see the red question marks, if that's what we're trying to find, we would be affecting all the weights, the activation function, the biases after. So it wouldn't work. We'd be changing one thing at the start, and then we'd have to change the things after it. We'd be affecting doing a loop that never ends. So we have to go from the back. We have to start finding the final bias, so the 2.61 firstly, and we work our way backwards. Hence the name backwards propagation, or also called backwards pass. So we're going to keep it simple. At first, we're just going to do a graphical example and try and find the B3 term at the end. So to find that final bias, we're going to have to map the inputs into our sum function at the end. So we've got the blue line, of course, on the top. So after that's times by the first weight, this first bias, the activation function, the second weight. The same thing applies for the orange one. And then in this next graph, you can see, well, it's only a transformation of the activation function, interestingly. But basically, the x-axis is the whole range of the inputs we're putting into our network. And of course, we've got the blue one, the orange one, and these are summed into our output, which is the green line. So you can see if we map it with our data points in light blue, you can see we're quite off. So we've done our weights, but they're still quite bad, like functions at the bottom. We've got the red lines signify the residuals, so that's the error for each data point. So you can see it's quite bad. So we need to increase our bias odds. But by how much? So you can see here on this graph, on the bottom we've got the bias. So obviously you can see as we decrease it, our loss on the y-axis decreases almost to zero. However, well, as humans, obviously we could see, well, we just add 2.5, right? But with much complex examples, when we have loads of biases and weights, then we have to have a much more advanced method. So we use gradient descent. So firstly, for that, we have to find the gradient. So you can see in light blue, maybe a bit hard to see. We've got the gradient light blue. And so we find the gradient, and that signifies which way we should move. And we take small steps accordingly to that to gradually go down and down. So we hopefully follow that pink curve right down to the bottom of minimal loss. So if you've got any questions, I'll come around. Me and Tony hopefully will hopefully answer any questions you have. Yeah, I don't take breaks.
With the chairman.
Hello. Okay, bro. It's me. Hello. Awesome. So sorry, I think some of you guys got confused on the concept of we're starting from the back. So we're only finding the first one, but now we're going to go backwards again and find the previous set of weights. So these ones in the green before. I think there was also some confusion of where does these blue dots come from. So they're from the training set. That's the data you train on. So in this case, we've got just a simple example of probabilities of some kind of disease. So we have the ones on the bottom have a no, and the x-axis is the dosage of the medicine, and the top, the guy, I guess, got cured or something. So that's the training data in this example. Yeah, now we've done somewhat of a simplistic graphical explanation. We'll move on to somewhat deeper maths. It's okay, it's not too complex. So now let's represent this gradient descent function as an equation. So we start by, so we had the blue lines, and these are just going to be represented by that partial derivative on the right. So if you think about it, what we're doing was wiggling this weight on the bottom and seeing how far that the loss on the top goes. Now we times that by mu, which is the learning rate. So usually this is just a very small number, like 0.01, and that signifies how far that step is the next one. So here we've got how far from this x to another x. Usually it's very small, because if we have it too big, you can imagine, like let's say 1, from this side we go to this side, we wouldn't get anywhere. We'd never go down. So we take it in small steps, but of course there's a trade-off of if you do it so too small, it will take ages. So there's different methods of how far, it was black magic of how small that should be. Oh, and of course we've got the old weight, the W on the right, and we're taking this mu times the gradient. So we're changing this weight previously, and we get our new weight on the left. So now let's try and represent this graph as one equation. So of course our predicted output at the end is in green, and we've got this blue element here, which signifies the top path. So we're trying to find these weights in red. So that'll be W3 here, and F will be the activation function. So we've simplified it a little bit because we don't care what comes before this. We've computed this value from the training data. We've put our inputs here. We've got a value here. So this will be X, and we've applied function F to it, the activation function here, soft plus, and exactly the same for the orange path. And of course, we've got the final bias B3, which we found before graphically. So now let's represent the loss function. So if you remember from the start, it's called sum squared residual, or SSR in short. So yeah, our predicted value was in green from the previous one. And now we're just taking it away from the observed. And observed comes from the training set. Those all the data points we had in the graph at the start, we're just taking the difference from them. Of course, this could be positive, this could be negative. So we're squaring them to make it all positive, so we wouldn't be adding one and then taking away the other. It would be misrepresenting the loss. So we square it, and of course we add them all together by each pass, each training data point we have in the training data set. And finally, we've got the gradient descent, how to, oh, sorry, for that. And then so, yeah, we're trying to find this gradient, right, in red. So how do we do that? Well, we've got equations of the predicted value on the top right. Under that, we've got the loss again. So we can't find it directly, right? We don't know what the partial derivative. That's why we're going to go back to the chain rule. We know what the loss function differentiate is in SSR over predicted. We know what we can differentiate the equation of the network, which is the other one. So we differentiate the loss function. Firstly, within the bracket is just -1. We put that to the front, and then we take the differential power. Again, we times by 2, so -2 out front. And of course, sorry, the next term differentiated. You can imagine, because it's a partial derivative again, it's different from a normal derivative because we've got these other variables we don't care about, right? Because we're trying to find W3 here. So the orange bit and the bias all gets cancelled out. There are unknown variables we don't care about. So all that's left is x of x, which is what y signifies. So the exact same process happens for the orange path because it's the exact same network, right? What you're thinking is, why wouldn't this be all useless? Because we always get the same values. Well, that's why the weights that we initialize at the start have to be random. It's important that we have different values for each of these paths. Because we have the same values, we'd always be doing the same calculations, and their usefulness would always be the same, right? It should be the same as having one path. So it's important to have the weights initialized to be random in some kind of range. And of course, we do this again and again and again. We do this firstly for each of the data points in the training set, and then each epochs, which we'll kind of describe in the code later. So interesting differentiation is the difference between backpropagation and gradient descent. So backpropagation is only calculating that one gradient, or the one blue line. So we do the full one forward pass. When you give one data point, you get that one gradient. The gradient descent kind of takes the average of multiple passes of these. So we represent it through multiple. So when you have the backpropagation, it takes in one data point from the training data set. So gradient descent covers the whole training data set. And there's different types. We've got batch, stochastic, and mini batch. So batch is most efficient because it can be parallelized. We can do it all at once. So we take, let's say we update the weights only after. So we do it all at once, let's say, and we update it after. So we give the whole training data set to the GPU, let's say, and it calculates all the backward propagations. And then only after that whole batch is processed, we update the weights. And this is opposite to stochastic, where after one backpropagation, then we update the weights, then go repeat the process again. So we're updating each time. So each next iteration depends on the previous one. So we can't parallelize it. So it's not as efficient, right? But it's more robust because we've got, I guess, fresher information from the data set, right? We're updating it more often with the more data we process. So mini batch combines both of those approaches. We've got smaller batches, and we do like the same process of updating it one, like let's say 10 at a time, right? So short break. I'll come again around any questions you may have, and we'll get back to some coding after. I mean, I was surprised with everything.
I don't because I like to use the cursor to move around. Do you walk around the eagle?
Like it's easier to get maybe ask questions.
Yeah. Walk around the room, make it more interactive, make it more energetic. Try to make the content more complex. This doesn't mean more math, this means more the concept. Me too, please. Yes.
I told you.
You switch off. Hi. Hello. So we had a good question. What relating the difference between backpropagation and gradient descent. So I think there was some confusion with that. So one backpropagation is, so we found in the first, I guess, graphical example, we found the equation of how the partial derivative for, let's say, the last bias. With layers, of course, you saw that one partial derivative here is the same one as this one, right? So basically what computer does is go backwards. So it finds the partial derivative of the last bias, the weight before that, then the bias before that one, and then the first weight. And all of that work is one backpropagation. But only has to do it once because all the partial derivatives stay the same, right? So you work out the partial derivative. That will basically be done at the start. And then each backpropagation after that, you just put in different values of the new weights, right? And they get updated. And that'll be that's all one backpropagation. You get that gradient. Or basically you get the updated weights. All the updated weights at the end is one backpropagation. And gradient descent is basically taking multiples of those backpropagations, doing it again. So because but one backpropagation, remember, is on one data point. And on gradient descent, we take in, with stochastic, only take one. With batch, or let's say we had an example of 100 data points in our training data set. So batch would take all 100, compute all the weights, and then update the network. Stochastic would literally only take one data point. Of course, the order is always random. You have like a seed at start for the random, like a random number generator, and it picks a given weight. So you only pick one at a time. With stochastic, you actually take all 100, and mini batch blends that, where it takes, let's say, 10 at a time, updates the weights, takes another 10 and another 10. So yeah, that's the difference between those. Hope that cleared up some confusion. Now we're going to get into coding. So we're using Keras, which is the library that TensorFlow uses. You might know PyTorch as well, but Keras is slightly simpler. Let's code. So first we're using this example data set called Pima Indians diabetes. So it's just some population and some kind of data on diabetes. We're not really too worried about that. So that just, we get a function from NumPy that nicely reads the CSV, splits in every comma. So the comma, of course, because it's CSV, we set the delimiter to a comma, signifying each column is split by a comma. And that just gets loaded into object data set. Then, of course, we've got X and Y. So these are objects. Let's say, remember, Y equals mx plus c, right? The Y is your output, the X is your input. So there's the same way, X is always your training data set, and Y is your testing data set. And all these brackets do is select a certain amount of columns from that CSV we had. So next we go into Keras. So first we define this model object as sequential. So that just says that each line after this will just be a whole separate layer, because I'm guessing there's different types of networks. So then we just add another dense layer. Importantly, the first one you have to give the input dimension. So that will basically automatically define the size of your input. So the first one's 12, 8, the last one's 1. So the first two hidden layers are using the ReLU activation function. So that's very similar to R1, but they just don't have that curve. They just have two straight lines, like that. Any difference between that is just, it's a lot easier to calculate than Soft Plus. There's no exponentials, just If it's less than 0, it's 0. If it's more, then it's just equal to itself. Then finally, we've got the sigmoid. So whenever you see sigmoid, it means it should shout probability. So our output, of course, is going to be one probability. So when you've got one output node. And with probability, we can't use the same loss function. So we're using binary cross entropy instead. And we're using this thing called an optimizer, called Adam. It's something that you need to define in Keras, but I wouldn't change it. It's really good at nearly every case, so I leave it alone. And of course, the final definition in that one is metrics. So this is what you're trying to measure to tell you how good your network is. So we're just doing simple accuracy. Now, does anyone know what kind of gradient descent this is using? So mini batch, stochastic, or just batch? Any ideas? Mini batch? Any other ideas? Well, it's a trick question. It's not using any of them because we've got this optimizer called Adam, and that basically changes the learning rate and the batch size each time. So it's type of mini batch, I guess, but it's constantly changing. So it's got this optimizer. And next we've got basically the fit function, which is just train this network. So we give it the training data set, the testing data set. We'll give it the amount of input, the epochs we want. So that's how many times it iterates. And then the batch size, and the verbose parameter, which I'm not sure what that does. And then, so once we've trained it, our models basically learn all our weights again, and we can do our normal forward pass fit in the previous workshop. So again, we're giving it our training data set X, and we're asking it to predict it. So it would give us an output between 0 and 1 because it's a probability. And we're giving it this random, just this threshold of 0.5. So if it was probability, of course, you could change this threshold. Let's say if there was, well, this is a medical test set. So maybe you'd want more false positives than false negatives. So you'd want to err on the side of caution. So maybe you'd lower that. So you'd get more people testing positive, let's say for COVID or diabetes. So they'd be more likely to take action after, right? Then let's say another use case of some non-significant industrial data that they don't care too much, is not critical, then he'd probably raise that or raise that threshold, and you wouldn't get as many false positives. And then, of course, at the end, we just a simple print statement. Yeah, this will be the industry kind of use case for it. But if you want to use the stochastic gradient descent, we just have to give it a different line. So if we're changing the compile, for our training line, we had the compile. So we're just giving it stochastic gradient descent, or giving the regular rate, momentum, which I did mention, and we're just giving that as the instead of the Adam optimizer, right? So that would be a different kind of training method. It wouldn't be as efficient because you wouldn't be doing that parallelism, right? You would be doing one each time, so it'd take a lot longer. But if you've got a CPU, I don't think there's much difference. So yeah, thank you for coming to our workshop. In 2 weeks, so this stays wrong. In 2 weeks, we've got a support vector machines, which will go deeper, some relating to these thresholds we've got at the end, and go deeper into kind of finding that threshold between your data points and how different use cases you'd like. And of course, it will be Alberto will be taking this one in 2 weeks, so hopefully see you there. And thanks for coming.
Goodbye, thanks. Do you have any questions?
Right, if you have any questions, come back at the end.
None whatsoever. Not one. Think it happened.
I thought that was good.
Put the little bug back. I don't know.
Oh, my voice started going and I couldn't tell that. Oh, Mike is muted. What is volume?
This isn't working.
My voice started going. Yeah. I think if you heard it, it just got deeper.
Oh no, I didn't. I thought this was
It was good though. Like some people asked really good questions on the second break, and then I basically answered them. With all that. So that was pretty sick.
I think,
We're definitely Sean.
yeah. To be honest, I don't really know what this one was about. I was trying to do like my part for it, like this poor vector machine. So now I'm like, okay.
Just wanted to ask what like a mathematician.
Yep.
What do not scientists do? It's like I thought they were like doing AI stuff, I guess, and they're probably doing, but
So like,
this was like 10 lines of code. So
yeah.
I guess there are like very smart people who
Well,
create those
this one's
libraries, but-
extremely simple, right?
Yeah,
It's
that's
like
fine.
basic, and because it's so basic, they just want to make it very easy, right?
Yeah.
So you have the libraries like PyTorch. I can't recommend the first TensorFlow from the start. Basically, that allows you to like, I guess you have a class. So you define like, have you done
Yeah.
Python before?
No.
But
I know. I mean,
Java maybe?
programming.
Yeah, so like classes. So you have to define the whole thing. Basically, you do that, and you do that for the whole data set. You do that for the whole model. So the model, you literally have to define the whole like
Like
forward
the
pass.
methods as well.
Yeah, you have to define the whole forward pass and the
Does it
initialization.
have it like benefits?
Yeah, because if you define a class right, you can customize everything. TensorFlow, you literally have to do the thing where they've just got a lot of methods, right? And you just have to pick the one you want.
That's why I was thinking, 'cause, like there are probably very like extremely smart people that work with these libraries and stuff.
Yeah.
So like it's only a small percentage of people that do things that do like.
Like data science, I'd say, I think it's a misconception. They don't do as much machine learning.
Yeah.
There's only the big companies that do real machine learning, because nobody else has the amount of data that you kind of need for it. So if you want to do like data science, you probably will do like statistics, the SVM stuff that we're going to do next week. So not as complex stuff, but like ML engineers, ML scientists, I guess they're called. Basically, anything ML would be at the bigger companies and be doing that.
Yeah, I see.
So I'd be more like I'm more interested like being an ML engineer, just somewhat like between the ML kind of scientist. They're still called data scientists.
Yeah.
But basically, if they're not in a big company, you have less data and you're usually doing more statistics, right? And basically, if you have like a data engineer, something like that, that's the ones that kind of program the infrastructure behind the scenes
Okay.
to kind of provide.
Having the training data.
If it's the infrastructure, it's like the coding stuff. That's what like the engineering team does. The data science focus on the algorithms itself, the maths behind it, the stats. And engineering does the back end stuff. So there's even within machine learning, you've got two different completely levels.
So apparently then there is difference in how do you write those algorithms, or like in which libraries do you use, or how much do you define each?
I'd say if you want like cutting edge, you want to go PyTorch.
Yeah.
If you want something more standard and easier, then TensorFlow.
Right, I see.
But yeah, TensorFlow uses Keras, so yeah, TensorFlow, Keras, same thing.
It was a fun conversation.
Cheers.
I like that. I understand.
Yeah, definitely.
Alberto,
And bro, we'll see probably, but tomorrow we'll see.
how do you stop recording it? Stop recording.